Hey everyone, this is Josh Lytle. This is my biodiversity presentation, and I chose to do mine on the mass and length correlations in common gray squirrels. So just to give you a brief overview of what I'm going to be covering. So we're going to start off with my hypothesis, the purpose for this experiment, and the overall prediction for the relationship between the length and the masses for the common gray squirrel. I'm also going to go over the methods for producing and analyzing just statistical data, in this case, and how it relates to length and mass. To go along with that statistical data, I used covariance and correlation. So we're going to go over those results as well as a scatter plot that I made that outlines the two variables pretty nicely. We're also going to discuss the data, and we're going to wrap it up with just talking about the limitations of the study and further ideas for future studies. All right, this is my intro. So the organism of interest, as I said before, was the common gray squirrel. Scientific name Squirrels carolinus. I probably didn't say that right. But the main purpose, as I said before, was just to determine whether the mass and length of a common gray squirrel are directly related, inversely related, or completely unrelated. And one of the key objectives in this was to just manipulate raw statistical data and to be able to put that into a format that is able to be manipulated and conclusions are able to be drawn from that. So the main question was, is the total mass of a gray squirrel dependent on the total length of the squirrel? So from that question, the hypothesis was made that if this biodiversity data is analyzed, the length and the mass will be directly related. So in other words, as the length increases, the mass also increases. So vice versa, if the mass decreases, the length would also decrease. And obviously, this prediction was made because usually the longer something is, the more it weighs. I mean, if you think about taller people usually weigh a little bit more than shorter people. With longer animals usually weigh more than shorter animals. So that was the basis behind the hypothesis. All right, let's go over my methods. So first off, an organism was picked and a hypothesis was formulated. So we could pretty much pick I think any animal, and I chose to do the common gray squirrel just because there was the most data on that. Then the biodiversity data was collected through a program called VertNet, which has a whole bunch of biodiversity data from all over the world. This data was then downloaded after sorting to include only the samples that had masses and lengths. This data was then uploaded into Excel, where we could actually see all of it lined out. There was, like 100 rows of data and about 500 columns worth of data. And that was after sorting to only include the masses and the lengths. Anyways, the Excel data was then manipulated and analyzed to view the correlation between mass and length. This analysis included correlation and covariance. A scatter plot was also used, as I said before. And precision and accuracy was maintained by filtering out all the incomplete data samples. So any data sample that, let's say that it had a mass but it didn't have a length or something like that, we just took out, and we were able to sort through that using the VertNet program. All right, so let's get into some data. So like I said before, there's a lot of squirrels in this data set. In here we had 443 total squirrels that each had a mass and a length. There were more that some did have a mass, didn't have a length. So we just included the ones that did have a mass and a length. So 443 total. The average mass of all of these squirrels was 526 grams. The average length was 454 millimeters. And in case you want to know the mass to length ratio, it was 1.16. So all of this data was in a ginormous Excel sheet, and it was then statistically analyzed using programs within the actual Excel. So within Excel itself, it has a data, it has an analyzed set. You can go and you can find like ANOVA single factor data analysis programs. I personally didn't do that because with this data you didn't have to, but for me I use correlation and I use covariance. So let's take a look at what that looks like on the next slide. All right, so here's our results. So as you can see from the top chart, the correlation data chart, you have length and you have mass underneath length, and on the top going across you have length and you also have mass. So this is talking about how length is proportionate to mass. So for correlation data, you never have a number above 1 and you never have a number below -1. So it's always between -1 and +1. If you get a number between 0 and 1, so a positive number, it means that the two variables are positively correlated. So we found that 0.441 was the positive ratio. So it means it was directly related and I'd say moderately influenced by one another. So length is moderately influenced by mass and vice versa. Now, covariance data is not a proportion. So it's simply a positive number or a negative number. And if you're wondering why there's a blank spot in the top, in the middle right-hand column, it's because that number is equivalent to the number diagonally to it. So the 0.441 is equivalent to the completely blank spot. That's just something that I found that's included in every covariance and correlation data analysis. But anyways, the covariance is a positive number. This tells us that the relationship between length and mass is directly related. If this number had been negative, this would have told us that they are inversely related. And essentially, correlation data is a little more useful in this scenario because it tells us the ratio of the relationship. Covariance simply tells us if it's direct or inverse. Okay, where its units don't really help us at all. But correlation, because it's a proportion, it can tell how related it is. If it's closer to 0, it's really unrelated at all. But because we're at 0.441, it's pretty related. It's not a whole lot related, but it's a little related. And that's pretty much what correlation can tell us in a nutshell. And this was the scatter plot I made of all the raw mass and length data. I just made a scatter plot of it. Length's on the bottom in millimeters, mass in grams is on the left-hand side, on the y-axis. And you can see that linearly, it's hard to tell. So most of these samples were between about 400 and 500 millimeters, and they all weighed between about 400 and like 700 grams. So you have a large percentage that are right in that area. Now some of the outliers, obviously you can see some of them weighed like 600 and didn't have a length. So I'm not sure who put those data pieces in, but it comes with actually using that program. You get all sorts of numbers. Some of them are outliers and you just have to take them out. Some of them just aren't as accurate as the other ones. Now we have an R squared of 0.161, sorry, excuse me, R squared of 0.1941, and obviously R squared, it represents the proportion of the variance of the dependent variable that's explained by an independent variable. So basically just the relationship between length and mass. So a larger R squared means a greater influence of mass from length. Now R squared is pretty small. So this suggests that our data, there's a weak influence between mass and length in using R squared and seeing how that tells us. Now, obviously, the number of outliers you can see on the graph definitely could have affected this, as like all along the bottom, the ones that have like no mass at all, and the ones on the top left, the ones that have a huge mass but no length, clearly could have affected our data a little bit, but it is what it is using this program. And for the most part, the R squared does suggest that there is a weak influence between the two variables. A weak influence in the two variables in a direct relationship. Let's get into the discussion. So in conclusion, statistically analyzing the raw data indicated that length and mass were found to be directly related to one another. And this was shown by the correlation and covariance data for mass and length, along with the scatter plot that was made that just took the raw data and showed that as the mass got bigger, the length also got bigger. So this also indicates that the hypothesis from earlier was supported by the data. And obviously the hypothesis was also supported by the covariance value, which I said before, and the correlation ratio. So let's talk about some limitations. Just from the data, it's impossible to tell if the samples were whole or not. So obviously this is a pretty big thing that we would need to know if the data is actually good or not. Because if you have a squirrel that got hit by a car, it might be a little flattened, and it's going to be a little longer than a squirrel that just, died of regular causes, or a squirrel that got half eaten is going to be, who knows how long that thing is, and who knows how much that thing weighs. So just off the bat, it's really hard to tell. And you can actually read through the data. It tells you where they found some of these squirrels, and some of them got hit by a car. Some of them were half eaten by like an owl, and it's really hard to tell. So obviously, the exact accuracy of this data isn't fantastic because we didn't actually collect the data. We're using other people's samples. These samples are from all over. So that's one limitation. Another limitation is that age and sex were not used in data analysis. So different ages, I mean, juvenile squirrels, they might have different length to mass ratios, different sexes. I mean, male and female could be genetically different in regards to mass and length. So we could have extended this this study and we could have made it more in depth. However, for sake of trying to have as many data pieces as possible, I chose to just make it simple and use as many samples as we possibly could. Another limitation is the different altitudes might have skinnier or heavier squirrels. At a higher altitude, you might have skinnier squirrels just because it's hard to get a lot of food up there, and the oxygen level means that your metabolism is a little bit lower. But this was not taken into account, so obviously because it wouldn't have provided enough samples to run statistical analysis, as I said, for the age and sex. So it is what it is. In future studies, this is definitely something we can elaborate on, but these are just a few limitations in this particular study. So some questions that came up when I was actually doing this study. Number one, how do we deal with squirrels who don't have any mass or length entry? I just chose to just not include them at all because I thought I don't want to infer how much they weigh or try to do like a proportion and then guess. It was just easier to simply just things that didn't have a mass or length, we just threw them out. We kept going with the statistical analysis with the complete samples. Another question was what graphs should be used because we have these two independent variables, mass and length, and we wanted to see if they were related, but we didn't know if they were. And through some research, I found scatter plot definitely the best bet. I mean, I know about all sorts of graphs like bar graphs, like column graphs. This one was clearly the best, as you could see before. It just shows what we need to see in the individual data points, and then you can put a trend line of where where the variables relate to one another in a rough area, not exact, obviously, because the R squared was so bad. That might be due to our sample size and the samples that were outliers. So some further research ideas. One of them is, do squirrels tend to be lighter at higher altitudes? I mentioned that a little bit before. And do they tend to have higher length to mass ratios? I think that would be a cool one to explore if we wanted to in the future. Another one, do male and female squirrels differ in average length, average weight, average length to mass ratio? Would be cool to see how they're genetically different. And finally, do different ages of squirrels have different mass to length ratios? I just think that would be cool to see a juvenile squirrel versus like an elderly squirrel to see if they really differ in that area, and maybe they don't at all. I mean, a future study would help us see that. Just to wrap things up here, it's a final wrap up for you. It was found that in the common gray squirrel, length and mass were found to be directly related. This did support the initial hypothesis. Covariance of correlation, the two means of statistical analysis, were found to be positive, which indicated this direct relationship between those two variables. Some of the limitations we discussed were that some of the samples were not complete, so they were roadkill, half-eaten, etc. And obviously the accuracy of that was not great for our study, but that's okay. In future studies, habitat altitudes could be considered on their effect on length. We could also explore male versus female mass to weight ratios, and really a number of different things using the VertNet program and the biodiversity data. So that's all I have. If you have any questions, feel free to reach out, email me, talk to me in person, and thank you for your time.